Welcome to the data science interview exercise video. I took 8 commonly asked interview questions for this video. I'm going to give the questions firstly, and I will give the answers after. I will use chapters for this video, which means you can skip the questions if you already know the answer or not interested. You can skip to the question you want by scrolling or clicking the times at the description. Here is our interview questions for this video. I'm not going to read them one by one. You can stop the video if you don't want to directly go to the answers. I'm starting with the first question now.
Question 1. What is the difference of supervised and unsupervised machine learning? Supervised and unsupervised learning are two main categories of machine learning, and the main difference between them is the presence or absence of labeled training data. In supervised learning, the algorithm is trained on a labeled dataset where the correct output or label is provided for each example in the training data. The goal of the algorithm is to learn a mapping from input variables to the corresponding output variables. Examples of supervised learning tasks include regression and classification. In unsupervised learning, the algorithm is not given any labeled data, and the goal is to uncover hidden structures or patterns in the data. Unlike supervised learning, the output is not provided, so the algorithm must find its own way of grouping or organizing the data. Examples of unsupervised learning include clustering and dimensionality reduction. To sum up, the key difference between supervised and unsupervised learning is the presence or absence of labeled training data and the difference in the goals of the algorithms in each case. Question 2. What is the difference between normalization and standardization? Normalization and standardization are two techniques used to pre-process data in machine learning and statistics. While they both aim to transform the values of numeric variables so that they have a similar scale, they do so in different ways. Normalization is a rescaling method that maps the values of a variable to a range between 0 and 1. Normalization often used to scale variables that have different units or that have a skewed distribution. The main advantage of normalization is that it ensures that all the variables have the same scale, which can be useful for some algorithms that are sensitive to the scale of the input variables. Standardization is a more formal technique that transforms the values of a variable to have a mean of 0 and a standard deviation of 1. Standardization is often used when the variables have a Gaussian distribution, and it ensures that all the variables have the same mean and variance, which can be useful for some algorithms that assume a standard normal distribution. To sum up, the main difference between normalization and standardization is the range of the transformed values and the assumption about the distribution of the variables. Normalization maps the values to a range between 0 and 1, while standardization maps the values to have a mean of 0 and a standard deviation of 1. Question 3. What is the bias-variance trade-off? The bias-variance trade-off is a fundamental concept in machine learning and statistics. It refers to the tension between two conflicting goals, having a model that is flexible enough to fit the training data well, and having a model that generalizes well to new unseen data. Bias refers to the difference between the expected predictions of a model and the true values in the data. High bias models are oversimplified and have a strong tendency to underfit the data, meaning that they miss important patterns and trends in the data. These models have high training error and low prediction accuracy. Variance, on the other hand, refers to the variability of a model's prediction for a given input. High variance models are overly complex and have a tendency to overfit the data, meaning that they capture noise and random fluctuations in the data rather than the underlying patterns. These models have low training error but high prediction error on new unseen data. The trade-off between bias and variance arises because increasing the complexity of a model will typically decrease its bias but it increases its variance. The ideal model strikes a balance between these two competing goals, achieving both low bias and low variance. The optimal level of complexity for a model depends on the size and quality of the data, as well as the specific problem being solved. Question 4. What is resampling? Resampling is done for several reasons, including estimating the variability of sample statistics. Resampling can provide a more accurate estimate of the variability of sample statistics, such as the mean or standard deviation, than traditional methods that assume a certain distribution of the population. Model selection and validation. Resampling techniques like cross-validation and bootstrapping can be used to select the best model for a given dataset or to evaluate the performance of a model by testing it on multiple samples of the data. Dealing with imbalanced datasets. Resampling can be used to address imbalanced datasets where one class of the response variable is underrepresented. By resampling the dataset to balance the class, the model can be trained to be more accurate for both classes. In general, resampling can help you make more accurate inferences about population parameters, evaluate model performance, and reduce bias and overfitting in statistical analysis. Question 5. What is the law of large numbers? The law of large numbers is a fundamental concept in probability theory and statistics that states that as the number of independent, identically distributed random variables increases, their sample mean will converge towards their expected value. In other words, the law of large numbers tells us that the average of a large number of independent observations of a random variable will be close to the expected value of that variable. This is a key idea in statistical inference and forms the basis for many statistical methods. There are two versions of the law of large numbers, the weak law and the strong law. The weak law of large numbers states that the sample mean converges in probability to the expected value as the sample size increases, while the strong law of large numbers states that the sample mean converges almost surely to the expected value as the sample size increases. Question 6. What is the difference between lists and tuples in Python? The key differences between lists and tuples are mutability, syntax, use cases, and performance. Let's check these differences one by one. Mutability. Lists are mutable, meaning their elements can be changed after they are created. Tuples, on the other hand, are immutable, meaning their elements cannot be changed once they are created. Syntax. Lists are enclosed in square brackets while tuples are enclosed in parentheses. Use cases. Lists are typically used for collections of items that need to be modified, such as adding or removing elements. Tuples, on the other hand, are typically used for collections of items that should not be changed, such as a date or a point in two-dimensional space. Performance. Tuples are generally faster than lists, especially for operations that involve accessing or iterating over the elements. This is because tuples are simpler and require less memory than lists. Question 7. What is A-B testing? What is the goal of A-B testing? A-B testing is a statistical technique used to compare two versions of a web page, mobile app, or digital product to determine which version is better. The purpose of A-B testing is to determine which version of a product is more effective at achieving a specific goal, such as increasing sales, sign-ups, clicks, or other relevant metrics. In an A-B test, two variants of product are created, where one element is changed in variant B. These two variants are then randomly presented to different groups of users, and the user behavior and interactions with the product are recorded and analyzed. The results are then compared to determine which version of the product performed better in achieving the desired goal. A/B testing can help companies and individuals make data-driven decisions about their digital products and marketing campaigns by providing concrete evidence of which elements and features resonate best with their audience. By testing and refining different variants of the products, companies can optimize their conversion rates and improve their overall user experience. Question 8. What is the confusion matrix? explain the components of it. A confusion matrix is a table used to evaluate the performance of a classification model. It summarizes the predicted and actual values of a model's predictions and shows the number of true positives, true negatives, false positives, and false negatives. The four components of a confusion matrix are true positives, true negatives, false positive, and false negatives. Once again, let's examine them. True positives: the number of instances where the model correctly predicted the positive class. For example, in a medical test for a disease, the true positives are the number of people who actually have the disease and were correctly identified as positive by the model. True negatives: the number of instances where the model correctly predicted the negative class. For example, in the same medical test, the true negatives are the number of people who do not have the disease and were correctly identified as negative by the model. False positives: the number of instances where the model predicted the positive class incorrectly. For example, in the same medical test, the false positives are the number of people who do not have the disease but were incorrectly identified as positive by the model. False negatives: the number of instances where the model predicted the negative class incorrectly. For example, in the same medical tests, the false negatives are the number of people who actually have the disease but were incorrectly identified as negative by the model. A confusion matrix can be used to calculate various performance metrics for a classification model, including accuracy, precision, recall, F1 score, and others.